Hi guys, welcome to ACE Anesthesia. Today, the topic of our discussion will be gas laws in anesthesia. So these are the laws which are coming in practical applications in our everyday life, and it's important to know about these laws to know about the basics of anesthesia and its medical uses in our everyday life. So the gas laws which we'll be discussing in this video include Boyle's law, Charles' law, Gay-Lussac's law. We'll be seeing about Avogadro's hypothesis, little bit about adiabatic process, Dalton's law of partial pressure, about flows that comes into as Hagen-Poiseuille's law, Bernoulli's principle, Poynting effect and Coanda effect. So these are the important gas laws which we have to know in anesthesia. So coming to starting this lecture with what is a gas. Gas is basically the substance in the gaseous phase above the critical temperature. And then what is a vapor? Vapor is a substance in gaseous phase below its critical temperature. So what is critical temperature? Is the temperature above which the gas cannot be liquefied no matter how much pressure is applied is called as the critical temperature. Right? So when we are coming to these gas laws, so three important terminologies or three important things which revolves around these gas laws are volume, right? We have pressure and then we have temperature. Okay. So the gas basically revolves around these three things. So volume is basically the quantity of the substance. Pressure is force per unit area. So force is in terms of newtons and area in terms of meter square. So pressure is equal to force divided by area, that will be in terms of pascals. Okay. And temperature that is present is the degree of hotness or coldness of a substance that is actually measured in Kelvin, right? So having this basic knowledge about volume, pressure and temperature, we'll come to the first law, which is the Boyle's law. So what is Boyle's law? Boyle's law states that at a constant temperature, that is where temperature is constant, right, the pressure is inversely proportional to the volume of the substance. Okay, that is the Boyle's law. So it comes to as P1 V1 equals to P2 V2. So I'll be discussing about each of these law and its medical application simultaneously. So when we come to Boyle's law, what is the use of the Boyle's law? So in Boyle's law, it will tell us about how many liters of the gas is present within the cylinder. So let us take an example of this. Okay, P1 is the pressure which is 13,800 kilopascals, which is the pressure of the cylinder. And V1, which is the volume of the cylinder, for example, if it's a 10 liter cylinder. Okay, now P2 is nothing but 1 atmospheric pressure, which is 100 kilopascals. What will be the volume of the cylinder at 1 atmospheric pressure? So if we have to find this out, let's put it into equation. P1 V1 equals P2 V2. So what we have to find is V2. V2 equals to P1 V1 by P2. So pressure 1 is 13,800 into V1, which is 10, divided by P2, which is 100. So this comes out to be 1380 liters, that is 1380 liters. So this will be the volume of the cylinder at 1 atmospheric pressure or 100 kilopascals, right? So this is the Boyle's law. So we finished up with Boyle's law. So next coming to Charles' law. In Charles' law, we'll be seeing that under a constant pressure. So there's a mnemonic. Charles is always under constant pressure. So we can remember like that. So under a constant pressure in Charles' law, right? So pressure is constant. The volume of the cylinder or the volume of the gas is directly proportional to the temperature, right? So, V1 by T1 equals V2 by T2. So, what is the usage of Charles' law? For example, if we have, if we have like 1 ml of sevoflurane, so will produce about 200 ml of vapor at 273 Kelvin, which is nothing but 0 degrees Celsius. Now we have to know at an OT temperature of 20 degrees Celsius, which is 293 Kelvin, how much ml of vapor will be produced by 1 ml of sevoflurane. Okay, so we can put it into this formula where V1 by, so we have to find out what will be the volume, that is V2, right? So here V2 is equal to V1 into T2 divided by T1. So next we are having what is called as the Gay-Lussac's law. In Gay-Lussac's law, it is at a constant volume, the pressure will be directly proportional to the temperature. What is the usage is that, or the application is that, we know that the cylinders which are present, they are of constant volume. Now, if the temperature increases, then the pressure within the cylinders increase. So, this is of special importance in the storage of the medical gas cylinders, where they are stored in cold conditions and not exposed to sunlight. Because with exposure to sunlight, the temperature may increase and hence the pressure within the cylinder may increase, causing the bursting up of cylinders. So, this is the application for the Gay-Lussac's law. Next, we come to the Avogadro's hypothesis. So, according to Avogadro's hypothesis, what it states is that equal amount of gas contains same number of molecules, okay, at standard temperature and pressure. Okay, so equal volume of this gas will contain the same number of this molecules at standard temperature and pressure. So what is standard temperature? Standard temperature is 0 degrees Celsius and standard pressure that is present is 1 atmospheric pressure. So at standard temperature and pressure, so 1 mole of the substance, okay, that will be containing, that will be equal to the molecular weight of the substance, that's equal to 22.4 liters. Okay, so this is the Avogadro's hypothesis. So coming to the application of this Avogadro's hypothesis. It will tell us about amount of nitrous is present within the cylinder, right? So as we know that nitrous is N2O, the molecular weight of this nitrous will be 2 into 14, which is the molecular weight of nitrogen, plus 16, which is molecular weight of oxygen. So it comes up to total of 44. So nitrous is having a molecular weight of 44. Okay. So 1 mole of nitrous, that will be containing 44 grams of nitrous, which is equal to 22.4 liters. So 44 grams contains 22.4 liters. So let us stop here. So when we take a nitrous cylinder, the weight of the nitrous cylinder, usually excluding the tar weight, comes up to about 2.2 to 2.5 kg. So of convenience, we'll take about 2.2 kg, right? So 44 grams will be containing 22.4 liters. So 2.2 kg is nothing but 2200 grams. How will we know about 2200 grams will contain how many liters of the nitrous? So if you put it as X, so X equal to 22.4 into 2200 divided by 44, which comes out to approximately 1120 liters. So this is how we find out the amount of nitrous which is present within the nitrous cylinder. Okay, one more application where we can see about the various gas laws till now which we have studied, that is the Boyle's law, Charles' law and the Avogadro's hypothesis, which is clubbed together, is to know about how much ml of sevoflurane is required for conducting a particular case, and also coming to the cost of the sevoflurane approximately. So how do we determine how much ml of the sevoflurane will be required for a particular case and what will be the cost that will be our expenditure in view of the sevoflurane? So let's see sevoflurane that is present, its molecular weight is 200 grams. Okay, so according to Avogadro's hypothesis, 1 gram of sevoflurane, that's equal to the molecular weight of the substance, which is 200 grams. That is equal to 22.4 liters or 22,400 ml. So what we infer is 200 grams of sevoflurane will produce about 22,400 ml of vapors. Okay, so 1 gram of sevoflurane will produce 22,400 divided by 200, which comes to 112 ml. Okay, so density of the sevoflurane, which is 1.5. So 1 ml of the sevoflurane will be producing 112 into 1.5, which comes to approximately 168 ml of the sevoflurane at 273 Kelvin or 0 degrees Celsius, which is standard temperature. Now using Charles' law, how to determine how much ml will be there at 293 Kelvin. Okay, so putting this into picture where X equals to 168 into 293 divided by 273, which comes to approximately 180 ml. So we have got finally that 1 ml of sevoflurane liquid will produce about 180 ml of this vapor at room temperature or at the temperature of OT, that is 20 degrees Celsius. Okay, now if we are conducting a case where we are using about 2% sevoflurane, okay, and the flows are about 6 liters, how much ml of this vapor is produced? Okay, vapor that is produced is approximately 120 ml per minute. Okay, this will be the amount of vapors that is produced per minute. So if we have to convert it into hour, it will be 120 into 60, which is 7,200 ml of this vapor per hour. Okay, now we know that 7,200 ml means how 7,200 ml of vapor per hour means how much ml of liquid? So we know that 1 ml of the sevoflurane liquid will produce about 180 ml. Okay, so by using this formula, so 1 ml will produce 180 ml of vapors. So how much ml will produce 7,200 ml of vapor? So putting this Y into picture, it comes as 7,200 divided by 180, which comes to approximately 40 ml, right? So each, how do we calculate? So this is how we got to know that for a 1 hour case, if we keep 2% sevoflurane at a flows of 6 liters, we will require up to 40 ml of sevoflurane to be used. Now, how can we calculate the cost? Usually, sevoflurane, which comes as a 250 ml bottle, will be having a particular cost, say about 7,500 rupees, okay, in Indian currency. So 1 ml will be approximately 30 rupees, okay. So 1 ml which is present is approximately 30 rupees. So how much we are requiring? 40 ml. So 40 ml is equal to 30 into 40, which is 1200 rupees. So this is how we have clubbed together the Avogadro's law, Charles' law together and come to the conclusion of what will be or how much ml of sevoflurane is being used for a case at a particular, that is for a particular duration, and also what will be the cost of sevoflurane that may be required for this case, right? So this is one of the important calculations which you all have to know, because it in fact is very important in practical life that you must understand to know how much ml is required for conducting a particular case. Next we come to adiabatic process. So what is adiabatic process? It is the change in the physical state of this gas without any, that is change without any heat transfer from to and fro from the surroundings is called as the adiabatic process. So what is its medical application? That whenever we are compressing the gas and suddenly, for example, in a gas cylinder, it's a compressed gas and suddenly we open the cylinder at high or very fast, it comes out through a narrow tubing. So what happens that because of this high pressurized gas coming through a very narrow tubing, there is very less time that is present for heat dissipation. So what happens that in this time there will be very high rise in the temperature. So if there is some grease or dust that is present at the nozzle or opening of the gas cylinders, this may cause combustion, right? Opposite to this is whenever like a gas is compressed suddenly, there is basically sudden cooling, and this is followed in cryoprobes. Okay, so this is the adiabatic process that we see and its medical application. Next, coming to Dalton's law of partial pressures, where the total pressure will be the sum of the partial pressure of individual gases. It is seen in our daily life, like when we inhale the gases, the total pressure will be a total pressure of the gases will be composition of the partial pressure of each of these gases. Okay. Next we come to flow. Flow, that is basically associated with what is called as the Hagen-Poiseuille's law. Right, so in Hagen-Poiseuille's law, what is flow is basically the quantity of the substance which is passing through an area per unit time. Whenever we see flow, the flow that is present can be of two types. We have laminar flow and we have the turbulent flow. Okay, in laminar flow, when we see, if this is the tubing, the flow will be very close to the pipeline. Okay, and it will be slow and without much of turbulence. So this is the kind of flow that is called as the laminar flow. Whereas turbulent flow, you will see many eddy currents that are produced, that is called as the turbulent flow. So when we come to the flow, one important law that is present is called as the Hagen-Poiseuille's law, which states that flow will be dependent on pi into pressure difference, radius raised to 4, and inversely proportional to the viscosity and the length of the tubing. So how is it having a medical application? Whenever we have to resuscitate the patient very fast. So we have to have some channel which will have a high flow. So how will the channel have a high flow? Number one, it will have a higher radius, that is a wider gauge. And second will be shorter will be the length. So that is why a wider gauge peripheral IV line will be better for fluid resuscitation compared to a central line. Other ways by which we can increase the flow is by increasing the height of this IV stand or by giving a pressure bag, which will create a pressure difference so that we will be able to resuscitate the patient faster. Other application of this laminar flow where it is present is in conditions like post-extubation group, where there will be lot of the flow of these turbulent gases. So in such patients, we give what is called as the helium and oxygen mixture that will reduce the density of the substance. So if the density is less, the flow will be better. So this is how the heliox mixture will help in post-extubation crew, right? So after this, we will come to what is the turbulent flow. When we see a turbulent flow, there is many eddy currents that are produced. So what will differentiate laminar from turbulent flow is what is called as the Reynolds number. The Reynolds number will be directly proportional to the velocity, the density and the diameter of this substance. Okay, density and the diameter, and inversely proportional to the viscosity of the fluid. Okay, so directly proportional to the velocity, density and diameter, and inversely proportional to the viscosity. So Reynolds number, if it is less than 2000, it will be a laminar flow. Okay, more than 4000, it is definitely a turbulent flow, right? So this is how it we can differentiate between the laminar and the turbulent flow, right? So another application of the Hagen-Poiseuille's law which we see is in the flow meters. So in flow meters, usually at low flows there will be more of conical, right? They will be having a laminar flow at low flows, whereas at high flows they will be more of it as a turbulent flow. So in low flows, this is in high flows. In low flows, they will be following Hagen-Poiseuille's law, where the flow is dependent upon the viscosity of the substance, whereas at high flows, they will be following the Graham's law and they will be dependent on the density of the substance, because at high flow, they will be a turbulent flow, and low flow, it will be more of a laminar flow. Okay, so these are the practical applications which we saw of the Hagen-Poiseuille's law. Next, we will come to what we know as the Bernoulli's principle. So in Bernoulli's principle, whenever there is a flow of the substance and it encounters a narrowing, right, there is an increase in the kinetic energy, right, and there is a decrease in the potential energy to keep the total energy constant, and hence the flow will be increased across this narrowing. So this is the Bernoulli's principle. Okay, this is the Bernoulli's principle. So based on this principle, we have several of the apparatus that is present. Most common of them will be the Venturi mask, right? In Venturi mask, we would have noticed that the nozzle contains like a constriction. Okay, because at this constriction point, the potential energy or the pressure drops and the kinetic energy increases, which in turn causes entrapment of this air. Okay, this is the mask. This is the face of the patient. So this is the Venturi mask application. Similar will be of nebulizers, of vaporizers, and all, they'll be following what we call as this Bernoulli's principle. Okay. Next we come to what is called as the Poynting effect. So Poynting effect means whenever there are two gases of different critical temperature. For example, in this case where we see of what is called as the Entonox. Okay. So when this is a combination of oxygen and nitrous. So oxygen is having a critical temperature of about 119 degrees Celsius, whereas nitrous is having a critical temperature of about 36.5 degrees Celsius. So the mixture of both of this, which is Entonox, will be having a critical temperature which is above that of the critical temperature of that of this lower gas. So that is it will be having a separate one which is called as the pseudo critical temperature. So Entonox will be having a critical temperature of about -6 degree Celsius. So what is the application of this? So what happens in Entonox is that usually they will be in a cylinder containing nitrous and oxygen. They will be in a gaseous state at room temperature. But when we go to very cold places where the temperature falls below -6 degrees Celsius, what happens is that the substance, that is oxygen and nitrous, separates. So nitrous being a liquid falls down and oxygen will be above in the cylinder. So when we give such a cylinder to the patients at colder climates, they will be first inhaling oxygen, which is completely okay. But later on, they will be inhaling only nitrous. That may lead to hypoxia. So that is why the Entonox cylinders, which are in colder climates, have to be rolled prior to use. Okay. So this comes the principle of Poynting effect. Okay. So one more law which I forgot to mention here, that is called as what is Henry's law. Okay. In Henry's law, we see that the solubility of any particular substance or the partial pressure of the that is the solubility of the substance will increase with increase in the partial pressure of the substance. That is, if the pressure is increased, the solubility of the gas as the anesthetic liquid also increases. Okay. So example of this is seen in case of deep sea divers, where when they go down and they go down and down more, the pressure will increase, causing increased solubility of the nitrogen. But when they come up very quickly, there is no enough time, and therefore the nitrogen will be blotted out in the form of bubbles, causing Caisson's disease or decompression sickness. Okay, so the treatment for this is in the form of hyperbaric oxygen, which will be increasing the solubility of this oxygen and also will provide an extra pressure for the nitrogen to dissolve slowly as well as steadily. Okay. So next comes to the last of the gas laws, which we'll be discussing in this video, which is called as the Coanda effect. So what is Coanda effect? Coanda effect is whenever there is like a constriction prior to a branching pattern, what happens, there will be a fall in the pressure and increase in the kinetic energy because of this, and there will be a flow of this gases beyond this constriction to only one side of the branches. For example, let's see if this is the mucus plug and it is present prior to this branching. So what happens is that whenever gas flows, it tends to stick to the convexity which is easily accessible, and there will be no gas flow to the other branch. So there will be unequal distribution of these gases. So this is called as the Coanda effect. So one more important application of Bernoulli's principle is seen in Petik's test, which is used to see whether the inner tube of the main circuit is actually intact or not. So this Petik's test I have explained in detail in the circuit systems. Please do see that video if you want to know what is Petik's test. So in this video, we have seen about the basic gas laws, that is the Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's hypothesis. We have learned little bit about Hagen-Poiseuille's law, about Bernoulli's principle, and also about Henry's law. Little bit what about adiabatic process, Poynting effect, and Coanda effect. So these are the important ones which I felt that we all must know, and also its applications in our everyday life. I hope this brief video was useful to all of you. Keep supporting. Thank you.